Hello and welcome to video 2 for acids and bases. This video is about all the math and setups for determining the construct and what's in an aqueous system of an acid or a base. So let's get right on started. So first we need to talk about the auto-ionization of water. In any sample of water, a small proportion of the water molecules dissociate to become equal concentrations of hydronium, H3O+, and hydroxide. And so because of that, we can take advantage of this presence of these in small concentrations to do comparison when they're not in perfect balance. If we take those two concentrations at equilibrium of any perfect water system, we find that the product of those two concentrations is equal to 1 times 10 to the negative 14th. And that's because each one of those concentrations is equal. This is unique to 25 Celsius, and that's very important because if you're not at 25 Celsius, the system's properties change and we can actually get a number other than this. But for our purposes, we'll stick with this unless the questioning or the line of questioning is about that specific change. So fundamentals of Kw, the ion product constant for waters, no matter what an aqueous system solution contains at 25 degrees Celsius, these two will be equal to that. So even if they're wildly out of balance, this product will always equal 1 times 10 to the negative 14. If the solution is neutral, they'll be equal. That's in the bracket there. If it's acidic, of course, you have a overabundance of hydrogen ions, and if it's basic, you have overabundance of hydroxide. Kw does vary with temperature, and this is what I was mentioning on the last slide. The cooler the water, the lower the temperature, Kw gets smaller, and you have less dissociation. And you have to think about what that would mean for your ion product constant. And then from warmer water, Kw would get larger. And so what that essentially means is your pH plus pOH operation doesn't necessarily always equal 14. And we'll get into that in class. General, how to use pH. Remember that pH is the negative log of the hydrogen ion concentration. And just for quick reference, if you see a value that's near a 1, that exponent pretty well guides you to pH. Okay, so just keep that in mind. We'll use this operation a lot, and you're quite experienced with it by now. When you're doing calculations and the system or the question asks and discusses a basic solution, and you do your math and you come up with a pH less than 7, you're wrong. Okay, the reality is you need to have a basic idea, sorry for the pun, of what your solution is, because when you form a solution or an answer to a question in acid base, you want to make sure that your answer is appropriate for the question. So for point of reference, and these are generalities, these are not absolutes, strong bases usually have a pH up near 14, weak bases anywhere from 9 to 13, and then basic salts from 7.5 up to about 12, and then the inverse of that for the acids. So you want to have a general idea of where these pHs should lie. And again, it's not absolute, and there's obviously room for overlap, but knowing that can kind of lead you from making a bad answer on a question that was otherwise not too difficult. Here's some common substances with pHs of notable ranges. Sig figs and pH values. Basically what this means is the number of decimal places in the log value should equal the number of significant digits in the molarity value. The number of digits after the decimal is the way this should read, so let's make that really clear. So let's say, for example, my log value was 4.42. Okay, these are significant digits. This is a placeholder. Okay, so this would imply that our molarity must have had 2 sig figs. Okay, so all the math operations we can possibly be doing, pH is the negative log of hydrogen ion concentration, and then its inverse would be hydrogen ion concentration is equal to 10 to the negative pH. pOH is the same with OH, with hydroxide transposed over where hydrogen was for the pH calculations. And we also will talk about pKa a fair amount, and that's just because it's easier to describe an acid's equilibrium concentration in terms of pKa than Ka sometimes. Same goes for pKb. These are all logarithmic functions. pH changes by 1 for every power of 10 change in hydrogen ion concentration. And pH decreases as hydrogen ion concentration increases. And for just a quick reference, a substance with a pH of 3 has 10 times hydrogen ion concentration as the substance with a pH of 4. This common association is tested to discuss the relative acidity of a solution. Again, K can change as temperature changes, but generally pH plus pOH is 14, just as the hydrogen ion concentration times the hydroxide ion concentration is 1 times 10 to the negative 14. And calculating backwards from concentration to get, calculating backwards from pH and pOH to get concentration is done thusly. pH of strong acid solutions. Calculating pH of strong acid solutions is simple. For example, pH of 0.1 molar hydrochloric acid is 1.0. However, if the acid concentration is less than 1 times 10 to the negative 7th, water then becomes the primary source of hydrogen ions in the solution, and the pH is just going to be 7, which is water's pH, theoretically. Keep in mind the pH of an acidic solution. If we say you have, you name it acid, its pH can't be greater than 7 at 25 degrees Celsius. Okay? So keep in mind, negative log of our value is going to give us pH, and any acidic system should be in an acidic pH. If you get something so dilute that it creates a basic pH, then water is going to keep your pH at minimum 7 if it's acidic. The sulfuric acid exception. If a sulfuric acid solution is more dilute than 1 molar, the concentration of hydrogen ions of the hydrogen sulfate ion must also be calculated. This doesn't happen on the AP test because you're going to have to do a quadratic equation to solve, but this is an exercise all of us should see at least once, so here we go. You should logically be able to predict that the 0.01 molar solution of sulfuric acid has a pH of less than 2, while a pH of 0.01 hydrochloric has exactly 2. And I want you to star this because we want to get you understanding why this is. The quick and obvious reason is just to state that, well, sulfuric acid is diprotic, so it's going to be more acidic than hydrochloric acid. That's true, but there's some more specificity to that. So what we're going to do is calculate the concentration of pH in a 1 molar solution of hydrochloric acid first. We know this is a strong acid, so there's no equilibrium to concern ourselves with. We just need the negative log of the molarity, and that's going to give us our pH of 0. So when we have a strong acid with a 1 molar concentration, negative log of that gives a pH of 0. So then calculate the pH of a 1 times 10 to the negative 10th molar hydrochloric acid. And this is the scenario where our system is so dilute that we get a concentration of, we get a pH of 10. However, this is an acidic system that's in water. The minimum hydrogen ion concentration this can have when there's no base present is 1 times 10 negative 7. So our pH of this would be 7. And that's because our acid is so dilute, only our water is making our hydrogen ions in appreciable concentrations. So calculating pH of weak acid solutions, you're going to have to set up an equilibrium. You'll write the balanced equation, and then you'll write the equilibrium expression, define initial concentrations and changes, and then determine the final concentrations in terms of some value x, and then substitute values with variables in the Ka expression to solve for x, just as we did in our studying of equilibrium. So there's nothing new here except that we're dealing with acids now in our equilibrium system. So here we go. Let's do one. Calculate the pH of a 0.1 molar solution of acetic acid. We know acetic is not one of our strong acids. Here is its Ka value. You'll probably know that in about a week. Won't forget it. So here is our written reaction. Here is our equilibrium expression with our Ka value. We do need to know the formula for acetic acid and how to dissociate it in the form of acetate and hydrogen ion. It's important that we have. Another name for acetic acid is ethanoic acid. Oops, there's an arrow. That's pretty funny. Well, I guess we'll figure out in a second what that arrow applies to. So we'll look back at the question. 0.1 molar solution of acetic acid. Okay, so we know that initially we have 0.1 molar acetic acid and no products. And then as we allow our system to come to equilibrium, we're going to lose some quantity of acetic acid, and the same molar concentration of hydrogen ion and acetate will appear. And so our equilibrium values are going to be these three, which we can then plug into our equilibrium expression. And this is the point we get to say, hey, what about our negligible x we learned in prior unit of equilibrium? Well, this digit can be viewed negligible again if it is less than 5% of 0.100, which would be 0.005. So let's see what we get calculating x with it as it is now. So there we go, simplified, and there we go, solved. So 1.3 times 10 to the negative 3 gives us a value that is certainly less than 5 times 10 to the negative 3. So we take that value, our x, which was equal to hydrogen ion concentration, take the negative log of that value, and we get a pH of 2.87. And keep in mind, this is a weak acid, and so ask yourself, is 2.87 an appropriate pH for a weak acid? And the answer is yes. There are 2 sig figs here because there are 2 sig figs in the stem of my concentration value. So I have the same number of digits after the decimal as I have sig figs in my concentration. So again, this just reiterates why that x was negligible. We always must check to see if, when in the scope of the course, we have to check and see that our x's we neglected were in fact negligible. So measure against your 5% of what was being subtracted from or added to. So here's a quadratic formula question. This is calculate the pH of a 1 times 10 to the negative 4th molar solution of acetic acid. The Ka is given again. So apologies for the preview on slide parts, but this is what we need to see anyway. There's our balanced reaction here and our Ka expression above, and then your equilibrium is written in there. Now each part is equal molar, and so we end up with an equilibrium expression that looks like this. We have all of our parts embedded, and we have a minus x on bottom, but you should note that this is a very small value we are subtracting from, and that's going to hurt our chances of neglecting x. Sure enough, sure enough, when we neglect x, we get 4.2 times 10 to the negative 5th, which is barely 10% of this, if not more. It's almost half of that. So we can't neglect x, and since we can't neglect x, we build our polynomial, set it equal to 0, and then plug into the quadratic formula. You can do this with nsolve on your calculator. You can also do it by hand. Either way is fine. When you solve for x in this situation, we get x is equal to 3.5 times 10 to the negative 5th. Note the significant difference in that value and this value. Those are pretty significantly different values given such small numbers. So it's important we did not neglect x here and use the quadratic formula. We can ignore this because it's negative. We then plug it into our pH formula, negative log of that concentration, and we get a pH of 4.46. Now ask our question again. Calculate the pH of a very low molarity solution of acetic acid. It's an acid, it's weak. It's also very dilute, so this stands to reason. It's still acidic, but its pH is quite high for an acid. Okay, let's talk about polyprotic acids. Whenever we're calculating pH of a polyprotic acid, we have to dissociate them stepwise, 1 proton at a time. And each stepwise dissociation reaction gets its own Ka value. As each hydrogen ion is removed, the acid gets weaker and therefore has a smaller Ka. And then as the negative charge on the acid increases, this is also an active force to help keep that extra proton, or to keep the protons that are still on the molecule. This is an example of a first and then a second dissociation. So generally, polyprotic acids are weak, but sulfuric acid, you should know, is a strong acid first in its first dissociation, then is weak after that. Generally speaking, whenever you get a polyprotic acid and we're asked to calculate pH from it, we work only with the first Ka value. And the reason is the first dissociation in the event you have a polyprotic weak acid is going to be significantly contributing to your solution. And any additional dissociation here and here from Ka2 and Ka3 is not going to contribute in a significant manner to your overall concentration and pH. So you can generally ignore a second and even a third dissociation in a weak acid. And that's explained here. Because sulfuric acid is a strong acid in its first dissociation and then weak, we have to consider both of those dissociations. Now we're going to work it here, but it's not on the AP exam. So here we go. Calculate the pH of a 1.00 times 10 negative 2 molar sulfuric acid solution. Here's the Ka for the second dissociation. Note that's still a pretty high Ka. So here's the dissociation reaction. Before this, what I've got here for you is called a before change after chart. This is just charting general stoichiometry so you can rationalize what must have happened in this complete dissociation. This is not an equilibrium system, so don't think that's what this is. We can assume it's a 1 liter solution and just call these moles if you want. Either way is fine. Just note that when this whole thing dissociates, we're just saying that we're going to get this and this in equal concentrations or equal amounts. And so then at equilibrium, you've got these two values for the amount of each of those two ions. Now, since we can throw that right back into our 1 liter container, these are also molarities. What's going to happen is, because my first dissociation was complete, these things are already in my solution. And so for my second dissociation, I have to consider those forces. And so here's my second dissociation reaction. So hydrogen sulfate forming hydrogen ion sulfate. I've already got this quantity of hydrogen sulfate, so that's my initial value for the second dissociation. And then for my initial value for my second dissociation for hydrogen ion is what I was able to create after the first dissociation here. So I have no sulfate to start with, and we have a Ka that is relatively small. So we're going to get some dissociation in order to meet our Ka value here. Minus x plus x plus x, because they're all equal molar. And then there is our expression. The problem here is that we are subtracting by relatively small numbers on a relatively large Ka value. So we're going to have to consider and use the quadratic formula. So first things first, here's my Ka expression. Here's my fill-in. If you use the quadratic formula to build a polynomial and then simplify and set equal to 0, your quadratic formula will yield an x of 4.52 times 10 to the negative 3. Keep in mind that x value is your hydrogen ion concentration. Since you've got that value, if you take the negative log of it, we've added our original concentration and our concentration of our second dissociation together to get the total hydrogen ion concentration in the solution. Once those added together, we then take that value to negative log to get the pH of the solution. So finally, determining the pH of a mixture of weak acids, essentially what you need to know here is only the acid with the largest Ka value needs to be considered, because it's going to contribute by far the largest quantity of hydrogen ions, and therefore it's the only thing contributing an appreciable amount of hydrogen ion to the solution. Anything else from a weaker Ka is going to give a value that doesn't influence sig figs. So anyway, you'll focus on the pH of the most acidic substance, or the largest Ka, and ignore the others. Finally, determination of percent of dissociation by a weak acid. When you've calculated values in the dissociation of a weak acid, you can then calculate percent dissociation. And essentially is this equation here. Final concentration of hydrogen ions divided by initial concentration of acid times 100. And that gives you a good idea of percent dissociation, a more familiar value. When you dilute a weak acid, this is very important. Anytime you have an imbalance in number of moles, adding water to a weak acid solution is going to influence K and make it a Q. When you dilute, you're creating concentrations that go lower, and that's going to make your Q value smaller than K. When Q is smaller than K, the rate of product formation increases and equilibrium shifts to the right, and it returns the system to K. As you dilute the acid, percent dissociation of that weak acid increases. Here's a graphic saying that again. That's going to conclude video number 2 on calculations with acids, and stay tuned for video 3 where we talk about bases and salts.